Hi, welcome to this introduction to data structures and algorithms. So in this lecture, we're just going to look at what data structures are, what algorithms are, what are their importance, and why we should use them. So generally for this course, we're going to try to teach each other how to program efficiently. And we'll look at the various constructs that allow us to do so later on. But the assumptions that we take on as we come into this course are that you know some basics of programming and you can also write some simple programs. Because this course, whilst it's not really going to focus on a specific programming language, requires you to understand the various programming concepts. For example, the variables, the arrays, the loops, the flow controls, and whatever else that come with programming. So I just expected to know those concepts as well as to write very simple programs. So the objectives of this course are basically to learn about data structures and algorithms. So a simple definition of a data structure is basically how data is going to be organized. So a data structure is basically defining how we are going to store data in our system and how data is going to be organized as we work with it in our various programs and systems. Then when we look at algorithms, we are basically looking at the step-by-step actions that are taken when you are running a simple program. For example, if you are trying to add two numbers, what are the steps that are going to take? What is the step-by-step procedure that you're going to take in coming up with the program to add two numbers? That's what we call an algorithm. Okay, so an algorithm is basically an ambiguous sequence of steps to compute something, and we'll look at that in depth a little better on. Then there's also algorithm analysis. Now, algorithm analysis is going to look at how long an algorithm will take to solve a problem, as well as how much storage or how much space does it require for it to actually solve that problem. So in this course, we're basically going to look at these three things. We're going to look at data structures, how data is going to be stored or organized in our programs. The algorithms, these are the step-by-step procedures that allow us to compute or to come up with solutions to our problems, as well as the algorithm analysis that allow us to analyze the speed at which an algorithm computes, as well as the amount of space that it requires when it's doing its computations. So if you're going to have a good program, you need a combination of data structures and algorithms. So you need a combination of good steps to solve the problem, as well as good ways of storing that information. And on top of it all, we want to do that with the least amount of space used, as well as in the least amount of time possible. So what makes up a good program? So a good program is a program that runs correctly. So firstly, it needs to operate by actually doing its work in the right manner. So if we're going to ask you to maybe come up with a program that calculates the balance of a bank account after a person has withdrawn some amount, that program should do that computation correctly, and for us to call it a good program. So you need to come up with good algorithms that actually follow the steps to achieve this result in the most accurate way possible. The programs that are good also run efficiently. So they use time and memory in a very efficient way. They use the least amount of time and the least amount of memory possible. Good programs are also very easy to read and understand. So you have to understand that at times some programs that are programmed or coded by people are going to be supported or used by people who are other than those who programmed it. So if you give your program to someone else, they should be able to easily read it, understand it, and then implement it to whatever situation they want to use it for. A good program should also be easy to debug and modify. So if your program is easy to read and understand, then it makes it easier for people to correct any mistakes or to actually add more functionality to it by modifying it and making it useful. So the whole idea is to come up with step-by-step procedures, which we call algorithms, that you can actually use from one program to another and just make some minor modifications for it to be applicable in that situation. So if you're going to have a good program, then if that program is also going to have a good runtime, that is, it's going to have the least amount of time possible to run and achieve its result, then you have to make sure that you're using the right data structures as well as the right algorithms. So you need to make sure that your step-by-step procedures, which are your algorithms, are so efficient such that they use the least amount of time as well as the least amount of space. So this course will focus on solving problems efficiently. We're going to look at a number of algorithms that we're going to basically go into and try by all means to understand how we can come up with step-by-step processes to solve certain common problems in programming. And the idea is not necessarily for you to claim or memorize these programs, but it's for you to develop the art or the skill of coming up with ways or efficient ways of solving problems programmatically. So you need to always keep in mind that whenever you're programming something or coming up with a solution, you need to come up with a program that uses time and space efficiently. And by so doing, you will use the right data structures as well as the right algorithms. So let's just look at algorithms in detail. So what is an algorithm? As has been said before, an algorithm is a step-by-step recipe for solving an instance of a problem. So with an algorithm, you are following set steps, one step at a time, one step after the other to solve a certain problem. So every single project that a computer performs is an algorithm. Whatever a computer is doing, it's following an algorithm because it's following certain steps to solve that problem. And also, an algorithm should solve these problems in a finite number of steps. So your algorithm should not run forever, but it should run in a finite number of steps. That means it should use time efficiently, and it should terminate at some stage. An algorithm also states the actions to be executed and the order in which the actions are to be executed. So, for example, if we say we are going to calculate the balance of a bank account after a person has withdrawn money from that bank account, our algorithm should show exactly the steps being followed and the steps that are being followed after every step. So, for example, if the first step is to check the balance in the account and then to subtract the amount that has been withdrawn and then to recompute the balance and then store the new balance, then you need to show those steps in an orderly fashion, and all those actions to be executed need to be written or done in a chronological or sequential order. So finally, it's basically an algorithm is basically a set or a collection of clear, simple instructions on what to be computed and at what time, as well as where things needs to be stopped after all the computations have occurred. So in instance, a correct program or a correct algorithm will run in accordance with specifications. So if you are given specifications by your client to come up with a program that calculates certain values, or that an accounting package that calculates the profit and loss, then your program should work according to the specifications given to you by the client, and thus we can term it a correct program. And we have already defined an algorithm as well as a data structure, and those are the main things that we're going to use in this whole course. So this whole course, as has been said before, is about data structures, algorithms, and the efficiency of algorithms. Those are the three main areas we're going to focus on. So therefore, what is the importance of data structures and algorithms? So if we use data structures and algorithms, our programs become more reliable and easy to maintain. You have got clear and simple algorithms as well as efficient data storage structures, which make it easy for our program to work well as well as easy for us to maintain it. Data structures and algorithms also allow us to come up with well-known and efficient techniques for solving problems to produce correct and fast programs in the minimum time. So the whole idea is we want to reduce the amount of time that we develop as well as run our system. So when we are running our system, we want it to run in the minimum time, but also when we are developing that system, we want it to be done in the shortest time. So we need to already know certain constructs. We already should know the ways of efficiently coming up with our algorithms. We also need to come up with programs that are easier to modify. So when you've got understanding of data structures and these algorithms that are used, our program becomes easier to modify. And we also want to make it easy for other software engineers to use our programs, as well as to be able to modify them for whatever it is that they want to use them for. So now we want to come to you want to look a little bit more into space and time complexity, which is basically the analysis of algorithms. So we've already spoken about this, about algorithms and what makes a good computer program, and all these we have already looked at. So now we want to start at some of the properties of an algorithm. So some of the properties of an algorithm are as follows. Number one, an algorithm must be correct. So no matter what, an algorithm should be correct, because if it's wrong, it will produce wrong results. It must be composed of a series of concrete steps. So an algorithm, as has been said before, is a step-by-step procedure, a step-by-step sequence of solving a problem. There should also be no ambiguity as to which step will be performed next. So when you have got your steps that you're going to follow, it should be very clear which step is going to be executed after each and every step. So there should not be any confusion as to which step is next after you've finished executing a certain step. Also, these steps must be finite, so the number of steps that can be executed should be finite such that the program can terminate, and this algorithm should take 0 or more inputs. So there should always be an input that should be taken. For example, if it's about a bank account and withdrawing money, so the inputs could be the bank balance as well as the amount withdrawn, and then we compute the eventual bank balance. An algorithm should be efficient and flexible. That now speaks towards the issues of time and space management, which we'll look at when we look at time and space complexity. It should also use less memory space as much as possible. So there goes again the issue of space, as well as result in one or more outputs. So the whole idea of using an algorithm or a step-by-step procedure is to come up with a certain output. So it's a good algorithm should always have an output. So when you're developing an algorithm, there are basically about 3 steps that you follow. The first one is you devise the algorithm. So when you're coming up with your algorithm, you need to know the step-by-step processes that you're going to take. So you can actually take a piece of paper and start writing in ordinary words or in sentences the exact steps that are going to be followed. For example, if you're withdrawing money from a bank balance, the first thing is to say, number 1, check bank balance. Number 2, check the amount that wants to be withdrawn. Number 3, check if the amount that wants to be withdrawn is less than or equal to the amount in the bank. Number 4, deduct bank charges. Number 5, so you should have clearly stated steps that you can write in ordinary words in a sentence. And then you can also use pseudocode. So pseudocode is basically more like a fake programming language of yourself that makes it easy to express your ideas. So this pseudocode is basically whatever programming language which is fake, which you can come up with from your head, which is not specific to a certain construct. For example, it's not specific to Java or to PHP, but it's just ordinary and universal, such that when a person reads your pseudocode, they can then use it to develop that construct or that function or that program with a specific programming language. So the first step is to devise the algorithm by writing it down in normal or ordinary sentences. And then the second step is now to validate the algorithm. This is where you prove the correctness of the algorithm. So what you then do at this stage now is you take those step by steps and then you simulate them on paper. So for example, if it's a case of withdrawing money, you have to check if your algorithm is working correctly by probably saying, you know what, I've got $500 in my account, a person wants to withdraw $600. Can that happen? And then you follow your steps to see if the account will allow them to withdraw based on the properties or specifications given to you. Then thirdly, you now need to express the algorithm. So after you've devised it, you have tested that, you have validated that it is correct, you then go on to express it using a programming language either that has been given to you or of your choice, and then you express that in a program, and then you run it in a number or a finite number of steps. Now let's look at what is called the efficiency of an algorithm. Okay, just a moment. Let's look at the efficiency of an algorithm. Okay. So in an algorithm, basically the key things that we want to take away in this at this moment in time in our study of algorithms is that, number one, there's something called time complexity, and then there's something called space complexity. Okay, so time complexity is basically looking at how long does your program take to run and complete the task at hand. That's basically time complexity. And under time complexity, we have got compilation time, the time that it takes to compile the program, as well as run time. That is the time the program actually spends doing the computations and solving the problem. Then under time complexity, we also have issues to do with the worst case scenario, the average case scenario, isn't the best case scenario. So the worst case scenario is basically saying, given a certain a set of inputs for your program, how long, what is the maximum amount of time it will take to run and complete that computation? That is the worst case scenario. Then the average case scenario is just saying, what is the average amount of time that is required to run this program given a certain number of inputs? And then the best case scenario is saying, what is the shortest time possible that the program will run to give you the result of your computation. And then, so that's basically time complexity in short. We'll look at it in depth later on in the course when we finally do the computations of how we actually calculate time and space complexity. Then space complexity, we are looking at how much memory is actually required or is consumed by the algorithm as it does its computations to completion. So given that amount of memory, you then deduce how much of it is actually required. So you realize that there is a fixed amount of memory that is required just to store the program after it has been compiled. And then there's the amount of memory that is required by the program as it is running. So you know, when a program is running and there are certain information that is being produced and needs to be stored, that information is stored into memory, and that memory is now variable based on the amount of computations that are being done, as well as the amount of time, as well as the amount of inputs that have been given. So these are some of the space that is required. Some is just to store the instruction space, you know, the instructions on how to run the program after it has been compiled. Then the data space, which usually stores your variables, your data structures, etc. Then there's the environment space, which is used when the program is actually running to store each function code that has been done. All right. So, for example, in this iterative factorial example, you'll find that the space occupied is, for data space, we've got these variables I, N, and X. For environment space, we are going to use is almost nothing because the function is only run once. So because this is not a recursive function, the function is only run once. So when it gets into this for loop, it does all these computations. So in this factorial example, we can actually write this whole function in words and say, you know what, first thing is you accept a certain variable of type long, and then you go into a for loop, where in this for loop you then compute by taking the value that you have, then the value that you have, the value of n, and then you start iterating around that in the for loop until you get the final result. So that's basically factorial. So factorial, we'll look at it again when we are doing our space and time complexity. Then we also have recursive. So this one we have a bigger environment space, because in a recursive function we call the function recursively or over and over again. So you will require a bigger environment space or more storage to store the various function calls that are going to be called. So basically for now, that's what we can look at in terms of time and space complexity. Now when it comes to the problem solving phase, or when you're now doing algorithm analysis to determine its time and space complexity as well as if it's good, what you need to do is to code the algorithm and see how long it takes. Okay, so when you know how long it takes, you need to develop a model of a computer. I think what we can do in terms of this algorithm analysis is we'll look at it in depth when we are now working on time and space complexity at a later time. So for now, I think we'll end here, and thank you for listening.